Okay, you've been introduced already. So you're the one who should be green.
Green is better.
Yeah.
Green is better.
So you're one of the inventors of CHERI. So, well, you have the right to give your slides at the last minute. So that's fine, but please keep on time.
I exercise that right. Very good. Hello again. I was asked to say a little bit about the CHERI Research Centre. So we're kind of covering organizations working in this space. And in part, this is really an invitation to collaborate. So we'll tell you what we're doing and what we're about. But in the end, ultimately, it's you guys that we want to engage with. So please do that. All righty. So I just wanted to start actually by acknowledging the very large number of contributors we've had in what has effectively been the CHERI Research Centre for the past 15 years. So the Research Centre comes out of the groups here at Cambridge around hardware, software, formal methods, security, and so on. And we are not, as I sometimes say, particle physics in that this is only one page of authors, but we are trying, and we will get there, and we have no authors yet. But thank you, everyone. There's a sign outside thanking as well, and we'll say a little bit later during the reception. So in 2010, invited by DARPA, we put in a proposal to try and transform computer security looking at the full hardware-software stack. And I think probably 15 years ago, we didn't understand the implications of that nearly as well as we do now. I think understand a lot about computers. I didn't know them. But it was the start of a 15-year journey. And since then, we've been joined by a lot of other collaborators across industry and academia who've made really essential contributions to this. And so the question was kind of raised, as we exit the DSBD program, how do we support that growing ecosystem? And in some places, that's going to be research. And so, a particular focus of our work is research, although there's also things like standards and reference designs and so on as well. So that's kind of the situation we find ourselves in. So the Research Centre was created in 2025 with support from DCIT and EPSRC here in the UK. And we really had laid out three sort of general areas of mandate. So the first was to address gaps in research and standards and sort of education training. It was very clear that some of these things existed. The memory safety story is quite mature, generally speaking. The compartmentalization story, is a work in progress with respect to software models. As people who took the training yesterday around Chariot and CHERI and so on will see, there's some really great stuff there. But pushing that to the same level of maturity as memory safety is really important. As Alex Rebert highlighted earlier, there's an interest in improving the performance of temporal safety. So this is another area where we're actively engaged in research. I'll say a bit more about these in a little bit. We also engage directly with industrial partners who are building hardware and software. So we are often in weekly or daily communication with engineering teams at various companies, helping them work through design choices. Is it in their microarchitecture? Is it in their use and adaptation of operating systems? It's a really essential part of what we do because with an early stage technology, and I think CHERI counts as early stage in the sense it's, hand-holding isn't quite the way to put it, but I think what I would say is there are some things we haven't explained, right? And there are aspects of our design where we haven't drawn out the essential intellectual contributions into clearly expressed design principles in all places. And operating systems, for example, are a place where that's true. So working really closely with industrial teams helps us get the stuff to market both more effectively, but also maybe at all, right? It reduces the risk of engagement with the technology. And then the last area where we do a lot of work is around open source reference design. Certainly we've been talking about software and hardware is also a part of that. This is about making sure, again, there's really clear illustrations of our approaches and our designs, but also artifacts that can be picked up and used, which I think is a really important part of adoption. And we've seen that used very effectively, for example, by Microsoft's work around Chariot, where having open source hardware and software has influenced a very large community. So the starting point for the center, as I said, is the existing team. We have around 30 people who join our weekly CHERI conference call. I think probably the funding on the center is around 15 FTE or so. And then we have a whole bunch of PhD students who are supported by both other sort of government agencies, organizations, and most of them by our industrial partners, which is really greatly appreciated. Thank you to those companies that have helped us with that. It's essential. So where is there still research to do? Well, to use slightly US-facing parlance, there's the fundamental research, the applied research, and then kind of the standards and best practices. And I've identified a few of these already. But really, the fundamental research for us is about further developing aspects of the architecture that could become more mature. These might be minor refinements. For example, ARM's umbrella included several different candidate compartmentalization approaches in terms of low-level domain switch instructions. This is because we didn't know which was the right one, and ARM contributed very actively to helping develop some of those mechanisms. But on the path to standardization and uniform minimalist architecture, we want to try and down select. And so evaluating those kinds of design choices, they seem really minor, right? But they're actually quite important to achieving performance and simplicity, accessibility of the architecture, verification goals, and so on. But there are also much richer fundamental research activities, and these might be around, for example, how do you integrate CHERI with machine learning accelerators, right? There's a great opportunity there, really more around the compartmentalization narrative. When you have multiple agents working with multiple models, it's really important you be able to strongly argue that you don't have incorrect flows of data or control between those various components. And yet, CHERI was designed for general purpose computing architectures, not necessarily specialized microarchitectures. So we have a nice thread of collaborative research going on with Google. We have done for the entire history of this project. And this is an area where we can try and bring some of our understanding expertise, bring it together with their industrial understanding of the state of the art, which is really great. On the applied research side, one thing we have to do is go back, and as Brad was mentioning, we need evaluation of how these technologies are improving the state of the art in deployed systems. So we can go and do, for example, studies around the adoption of memory safety, its effectiveness, its performance working with deployed systems and industrial partners at a scale that was never possible before DSPD, certainly. And those kinds of activities, I think, are really important. There's also aspects of research still around optimizing the compiler toolchain to try and achieve the desired performance, right? These are, CHERI is disruptive for these technologies. Sometimes those disruptions are very surface, and sometimes they're quite deep. And where they're deeper, having that research understanding and contribution is really important. And then finally, when we talk about sort of standards and best practices, it means everything from how are we standardizing the CHERI extensions to the RISC-V architecture to the work going on in ETSI around memory safety standardization. How do we help trigger and support the expression of demand from government and for industry for these kinds of features? And there is research there because actually there isn't a good consensus on what memory safety is today. There are a lot of ideas about it, and trying to bring those together and convene the discussion is a research-focused activity, right? To an extent that maybe surprises even those of us who went in thinking it might be research. I think we're looking at some very productive results there, but it's been a serious lift to try and get to that. And then finally, documenting best practice around hardware and software. So I'll come back briefly to a couple of these. In terms of some exciting stuff we're doing, as part of DSPD and the last couple of years, we estimate we're now in excess of 200 million lines of open source C and C++ code that has gone from being distinctly memory unsafe to actually having quite strong memory safety. We would like to know what lessons we can learn from that. We spent in the original design a lot of time thinking about reducing friction. We tried some distinctly wrong paths that we had to try and work back from and change our approach. Now is a good moment to revisit those because we have all of these lessons coming out of DSPD to try and figure out how we can improve it. Can we improve the performance, the security, the compatibility, and so on? Another area that we care a lot about right now is around language runtimes for high-level managed languages. These languages offer great memory safety to applications written in them, and yet their runtimes are written primarily in C and C++ and are full of vulnerabilities. My favorite example of this was maybe 2 decades ago or something, but it was Ruby as a language does not have format string vulnerabilities, but Ruby software can implement format string related exploits because there was a type safety bug in the C and C++ implementation that allowed that C-level behavior to leak out into Ruby-level language interpretation. Language runtimes are among the most vulnerable pieces of software we have, and so the encouragement to use high-level languages is great, but we need to try and reinforce that with techniques like CHERI at lower levels. Another key focus I mentioned before is around maturing our software models for compartmentalization. The architectural features are now there, which is great, and we're working hard on several different approaches, seeing varying degrees of early deployment and experimentation. That's really useful to do. But around that, software compartmentalization is an engineering activity, unlike memory safety, where you can just throw it at the problem and hope for, with a little bit of effort, some enormous benefit. Compartmentalization is around how you structure applications and interfaces. So I think there's a big space for research in that space, which is underfilled right now, and it'd be great to see that filled not just by us, but other people. I've talked a little bit already about specialized cores and accelerators. I think one of the things that Google has announced is the inclusion of CHERI in their roadmap for future core NPUs. I think this is really exciting. I think there are some great research questions on the path to that getting out the door successfully, and those are things that we hope to engage with as well. And then I mentioned memory safety and demand signal. I think not just for memory safety, but for compartmentalization as well. For the perspective of ETSI, the approach that we'll currently look like we'll take is to consider compartmentalization a form of memory safety. But I think there's a lot more to elaborate about that, but it's really important we get those demand signals expressed, and there's research in doing that. One of the problems that was mentioned earlier is CHERI's behavior with respect to temporal safety. It has strong temporal safety, but in some workloads, the scalability is not there. We can see well in excess of industrial acceptable performance overheads for some specific kinds of workloads. These are high throughput heap reallocations. You might find these, for example, they're most critically demonstrated in the spec Omnet PP benchmark that people may have tried out. This consists of allocating vast numbers of nodes in a graph, computing on them, freeing, and so on. But you can also find it in things like network-related workloads where you have high packet throughput, and it's important that we optimize for those problems. You can always turn off temporal safety for those kinds of things, but obviously we want it on. So how can we adapt and develop new techniques for that? In some ways, this is a really essential research problem around capability systems because in designing CHERI to be compatible with and happy with contemporary, very decentralized microarchitecture, big chips, out-of-order designs, lots of cores, we focused on making access control cheap, but revocation comes in, therefore, as expensive. Right? So, and in our environment, use after free protection is, roughly speaking, revocation. So we have a whole spectrum of research activities. We have PhD students working on new kinds of architecture and microarchitecture through to very applied forms of research with close collaborations with industrial collaborators around measuring the actual performances results we see. A lot of the existing results in papers are early research results, right? That code was never seriously optimized. And so the ability to improve performance, even within the current architecture, is quite high. We're also interested in some of the other ideas coming out of research in the space. Recently, there's been a trend towards type-stable reallocation. Well, type-stable reallocation is a point in a larger temporal safety trade-off space. And it's one that could be combined with CHERI in certain use cases to allow us to trade off performance and security behaviors. Maybe that is appropriate for some of these high-throughput workloads, such as packets. Another area that we've been doing some specific activities around is communication. So this is partly about best practice, but also it's about teaching people about CHERI. CHERI, as with all technology, comes with limitations, and we have tried to document them in our papers, but actually we didn't have a centralized resource people could turn to understand the limitations of CHERI memory safety. And so one of the ongoing collaborations we've had with ARM and Bloomberg, with Google and others, especially on the adversarial side, has been to try and engage with those limitations and carefully document them. This is important because you should be honest about the limitations of your technology, but also we have a lot of people doing adversarial exercises against CHERI right now. They're saying this is going to be a deployed technology. Can we find holes and problems with it? And we don't really need to hear about the problems we already know about, right? What we want to hear about is the problems we don't know about, and I suspect that is also what the people performing those exercises want as well. So this has been an important activity as part of those adversarial collaborations. Mentioning software best practices, there are some things we just haven't written down, right? We spent a lot of time early in DSBD writing down what CHERI C and C++ were in a very practical sense, but we provided the trusted computing bases, such as memory allocators, as part of our software prototypes. Well, now we have this blossoming of OS support, Linux support, and SEL4 support, a bunch of embedded operating systems. We need to write down, properly analyze, and document a bunch of those trade-offs and provide that as guidance to third parties. So in terms of some of the stuff we've done very successfully in our first year, probably one of the greatest successes is collaborating with our industrial partners to get the RVY specification to the point where it is approaching ratification, right? There's basically a final draft being in architectural review with RISC-V International. I want to make sure we credit those industrial partners a lot, right? The likes of Codasip and Google and SCI and others were essential to this process. But we were able to engage with it from a research perspective and answer a lot of unanswered questions, also to document design principles that along the way we had developed, but not carefully documented. That becomes rationale for the design choices in the RISC-V context. And likewise on the ETSI front. Lifting forward open source software is something we've done in close collaboration as well. What we all want to land on the RISC-V side is a single, well-maintained, to go back to Andrew's thoughts, set of tool chains and operating systems. But it is a substantial lift to bring forward to the ratified design, and we don't yet have the final opcode encoding. So this will continue for a little while forward, but I'm hopeful that, within 3 to 6 months, we'll be in a place where all of those things have landed. I'm going to take my moment here to run over by a minute or two, but not too long, I promise. I didn't do it earlier. You had to be proud of me. Anyway, there are a couple of new activities I just wanted to advertise for this audience particularly. One of the things we're looking at doing is bringing up what we call like a CHERI seminar series. This will be probably monthly talks probably targeted primarily at an online audience, although we will host those events physically here in Cambridge. We'll be growing our focus around educational material, looking particularly to develop material for undergraduate audiences and possibly those younger than that as well, kind of see how far you can go with C language memory safety. But surely there is something to say about design principles and compartmentalization. And then trying to continue to flesh out the open source story, particularly with respect to hardware. I mean, one of the risks we identified in CHERI adoption is that we have some great work going on with specific cores. But when we talk to large-scale consumers of technologies, they want redundant supply chains. You can't have just one application core, just one microcontroller. You need them from multiple vendors, multiple implementations, multiple paths. And so supporting the CVA6 CHERI work coming out of Capabilities Limited, and also now in collaboration with Low Risk and Oxford, trying to get that to be an industrially stable and reliable high-performance design. And I think those kinds of activities are really essential, because you can't have consumers saying we can't use CHERI because we can't have a single vendor or possible failure in that supply chain. So with that, I'll wrap up, having taken my extra minute. And I guess I will encourage you to reach out with questions or chat with me at this event. We're here to help bring this technology to maturity now, and I think it's really a nice moment for that, and we are very happy to engage with and help people who are giving it a try. So thank you very much.
Thank you, Robert. And you're almost on time, so maybe what will I do with the extra time? Apparently we have some question online for Robert.
Oh, no. Okay. I thought I still have the mic, so it's fine.
Yeah, you still have the mic, so don't escape. Dan, can you read the question, please?
Sure, yeah. So we have a question from Andre, who says, what does increasing the adoption of CHERI-enabled systems mean for trusted execution environments? Is there ongoing research in this direction? And modern TEEs have been shown to suffer from a variety of security issues. Could it be possible to mitigate some of them on CHERI-enabled systems?
I think that's a great question. I think I would frame it as having two kinds of answers. So the first question is CHERI a complementary technology? And the second is CHERI the technology you should use to implement your TE infrastructure? So on the former side, I think, as you're suggesting in your question, obviously, yes, those TE software stacks suffer memory safety vulnerabilities. They would benefit from fine-grained compartmentalization and so on. I think those answers are very clear, but you'll need it in a microarchitecture and an architecture that supports TE features of the sorts you're already using. And that's certainly a viable thing to do, but I don't know necessarily how much TE stuff exists on the RISC-V architectures and microarchitectures that are currently being developed. So I think there's probably a straightforward story in how you do that. But the technological details, well, we'll have to work through. The second question is, should you be using CHERI for this instead of the existing architectural features? Now, I know there are a bunch of people in this community who do believe that that is very strongly the way to do it, that the compartmentalization technologies in CHERI are a better way to achieve these goals. I think there are some really important implementation questions around that. For example, to what extent are you able to get rid of your existing software stacks and replace them? Or to what extent do you maintain kind of like this ring-based structure? In our clean slate designs, we've done a custom OS that has these TE-like features, running with an MMU, but in a sort of very capability-oriented design. Are you able to push your entire software and OS stack in that direction, or is that more of the 20 to 40 year goal? So I don't have good answers for these, but I think there's a lot of enthusiasm. I do know that there is a plan to have a white paper out of RISC-V International on implementing TEEs using CHERI. Ben nods his head. So I hope that will be an excellent reference to answer this question. Yeah, there's been a lot of exploration and research. I think what we'd like is like the best practice engineering, part to that. And I guess a reference software stack would be really good.
And there's a working group working on
this could be true, which would be excellent. Yeah. Is that
Okay. Any question in the room? Robert? No, you're all quiet.
One more question if there's time. Sure, it's from Thierry, and he says, do you see any industrial future for CHERI outside of the RISC-V ecosystem?
I would think that is a complicated question that probably takes more than the time available. I think in terms of the technology, as far as we could tell, this appears to be applicable to all of the ISAs we've tried it. So that is from the ARM ecosystem. We did a prototype for DARPA a few years ago looking at x86. So I think in a purely technological sense, there's no reason that wouldn't be the case. I think the real question is how you take things to market. And what are the motivations that drive the kinds of organizations that build microarchitectures? It is certainly easier in the RISC-V space where you can have lots of autonomy to make local decisions and take risks. It's harder for these bigger companies. I'd like to think that our efforts, especially around memory safety standardization, the CRA, and so on, might be effective in trying to convince some of those vendors that it's a good time to bring a product to market. But ultimately, they're responsive to their customers. So our job is to go to those customers and try and convince them that they need to go to their vendors and say, this is what I want. So.
And this is one of the goals of the CRA, right?
I
To
mean,
have this
I think
cascade
it will be
down
lovely to
to
think
the,
that when we're done and the EU is done, the CRA is a tool for convincing people to use strong memory safety and compartmentalization at scale for everything. CHERI is certainly technology that can help with that.
Great. We have a question there.
Try not to
Hello.
wince watching this front.
Just a short question. Are there any plans for capability-aware DMA controllers, MMUs, and other peripherals?
Yeah, I mean, we've done a bunch of research prototypes in this space. I know that Microsoft, I don't know if SCI is currently using one. I know Microsoft did do work in this space as well in the chariot context. I think it is a very sensible thing to do. You want your DMA and your accelerators to all follow these rules as well. And I think the technologies to do it are not very hard to get to from where we are, especially in embedded systems, right, where there is some flexibility to replace the DMA engine rather than it being, you know, the one that came on the PCI card. So I think the quick answer is yes. I didn't have it in the slides, but one of the areas where we're trying to start to document best practice or develop and document best practice is around DMA and sort of I/O peripherals and sort of heterogeneity more generally. So.
Thank you.
And again, there's a working group for that. So, and Ben will talk about that tomorrow, in fact.
I sort of feel like I was a bicycle about that.
So, any more questions? Should we go to the next speaker? So, thank you
Sounds
again.
good. Oh, thank you very much.